rest of this chapter is devoted to energy in terms of gases and processes involving gases. So like our isobaric process, where pressure is held constant, volume and temperature can change. Isochoric process, where volume is held constant, pressure and temperature can change, so forth. So, conservation of energy. You remember we modified it slightly. Originally, when we were talking back in the energy chapter before, when we introduced energy the first time, all we had was that work was equal to the change in potential energy plus the change in kinetic energy. We didn't worry at all about energy transfer in terms of the room being warmer than your ball rolling down the hill, sort of thing. And we didn't talk about the actual energy of the molecules themselves, which was fine. On a macroscopic scale, there's nothing wrong with what we did. When we talk about gases, though, it's going to be very important to distinguish energy exchanged by work. Work specifically is mechanical, meaning you have actual physical forces being applied that are making things move. So work, still a transfer of energy by way of forces. Forces have to cause motion. So work, an example of gas would be like a bicycle pump, where you're pushing on the pump, you're pushing on the piston, you're applying an actual force, and you're making the gases physically move. Q is energy exchange because the system is colder or warmer than its surroundings. So there's actually energy exchange because the surroundings is at a different temperature than the system itself. And so energy will transfer between the two, trying to bring them to the same temperature. Now delta U is still specifically gravitational potential energy, so if we physically move our object vertically, or elastic potential energy if we have a spring. Delta K is still our 1/2 mv squared if we change how fast it's moving. The delta E thermal it's a type of kinetic energy, but on the microscopic scale. So all the little atoms, for example, in this room, all the little air molecules are moving around. They have a certain average energy. The delta E thermal is the change of that energy. It turns out the amount of energy the molecules have on average is directly related to the temperature of the room. If the room gets warmer, they're going to move faster on average. Okay? So delta E thermal is looking at the energy of the molecules themselves. Now, typically with gases, we're not going to take our bicycle pump and start throwing it up and down. Okay? We're not going to be pumping on it and running up a hill at the same time. Okay? We're not going to be taking the bicycle pump and running around with it. We're just going to pump it. So we're going to be doing work, for example, which can in turn cause the change in thermal energy. So in general, those two are not going to apply when we deal with gases. They certainly can. If you want to take your system and drive up the mountain with it, that's fine. You will change the potential energy, and it's easy enough to throw in. But in general, if we just have a system that stays in one location, it goes through its process, our conservation of energy equation will simplify to Q plus W is equal to the change in thermal energy. Now we're going to talk, we have some specific equations that apply for each different process. This equation as a whole is perfectly valid in all processes. This is actually called the first law of thermodynamics. The first law of thermodynamics is the conservation of energy equation. Whatever energy exchange you have due to heat, so temperature differences, whatever energy exchange you have due to work being done, has to equal the change in thermal energy. This is the internal energy of the system. Okay. This This equation must be satisfied regardless of the type of process you use. It doesn't matter if it's isobaric, isochoric, isothermal, or adiabatic. The energy must be conserved. Okay. Now, some basic equations we have. A lot of our equations depend upon whether our gases are monatomic or diatomic. We're not going to go beyond monatomic or diatomic. There are certainly gases out there that are triatomic and so forth. We're only going to look at monatomic versus diatomic. We have a set equation that works for the change in thermal energy for both monatomic and diatomic. They differ just slightly. For monatomic, the change in thermal energy is equal to 3/2 nR delta T. N is the number of moles. R is our universal gas constant. Delta T is the change in temperature. The only way you can change the thermal energy is if you change the temperature. Okay? Diatomic ends up being 5/2 nR delta T. And that is because of the degrees of freedom. You may have heard of that term before in chemistry. If you have just a single atom, it can move X, Y, Z axis. That's about it. If you have a diatomic molecule, they can move X, Y, Z axis, but they can also twist and rotate. So they have more types of energy they can possess, besides just the traditional translational kinetic energy. So the 5/2 versus 3/2 is just because there's more types of energy it can have, more types of kinetic energy. Okay, so that equation, those two equations are valid regardless of the process. So it doesn't matter if they're isobaric, isochoric, nothing. Those equations are perfectly valid. Another equation that works for both of them is our equation for work.
R was the what constant?
The universal gas constant is R. Now, work we know is force times distance. Technically, it's the integral of force over a distance. So, with gases, we don't tend to talk about force, we talk about pressure. Pressure, remember, is force over area. We can write work in terms of pressure. It is going to be the integral of pressure with respect to volume. But we have to be kind of careful here. We want to use the same definition of work as we used before. Positive work meant we put energy into the system. Negative work meant we took energy out. We want to use that same relationship here so that we're still working on the same page. If you think about a bicycle tire, the pump, bicycle pump. As you apply that pressure, increase the pressure, what happens to the volume? Decreases. You compress it into a smaller volume. dV will be negative as pressure is positive, giving us a negative value, but we don't want that because if we apply pressure as we push on the bicycle pump, compressing the gas into a smaller volume, we're doing work on it. We're putting energy into it. So we want the value to be positive. So we need a negative sign in our equation to balance out the negative sign we'll get as the volume gets smaller, so that overall we get a positive answer as we apply the pressure and make the volume decrease. If we pull back up on the bicycle, the handle, increasing the volume back up, the pressure will decrease. So we'll get a negative answer that way. That equation works quite nicely. If you remember, we talked about a little bit about the PV diagrams, where we graph pressure versus volume for different processes. For example, an isobaric process was one that we had a horizontal line because the pressure stayed constant. If I have a graph of pressure versus volume, work is the negative integral of pressure with respect to volume. Graphically, what is the integral? The area under the curve. So if we find the area under this curve and negative. So the negative area under the curve will give us the work. So if we have the PV diagram, we can find the work graphically, or we're going to have to integrate. It depends upon this process we're going to look at. Okay. We're going to add to your list on our processes. We had a couple equations that we use the ideal gas law to come up with some relationships for each. We're going to add to them. Remember, isobaric process is one in which the pressure is held constant. Pressure is held constant, so that means if you change the temperature, the volume will also change. If you increase the temperature, you'll increase the volume. Nice thing is, if pressure is constant, that comes out of the integral sign. Integral of dV is just delta V. So the work is actually quite simple to determine in an isobaric process. It's simply the negative P times the change in volume. Final volume minus initial volume. So work, really easy to figure out. Turns out we have an equation also to find Q, the heat exchange at constant pressure. Q, if you remember before, we were using MC delta T as temperature changed. With gas, we don't tend to talk about the actual mass of the gas, we tend to talk about the number of moles. So we can use N times what's called the molar specific heat. So instead of joules per kilogram Kelvin, it's going to be joules per mole Kelvin. So it's still the amount of energy needed to change the temperature by 1 Kelvin, but it's now per mole rather than per kilogram. Molar specific heat, there is a very unique value for the molar specific heat if pressure is held constant. We use a capital C with a lowercase subscript of P to represent it. That's called the molar specific heat at constant pressure. It has a different value whether we are using a monatomic or a diatomic gas. Oops. For a monatomic gas, the molar specific heat at constant pressure is 5/2 R, where R is 8.31, the universal gas constant. For the diatomic gas, it's 7/2 R. The units will be the same as what R is, so joules per mole Kelvin.